All right, so in this video, I will derive the electric field expression for a finite rod, but above one of the ends. So let's draw an infinite rod right here. Oh, I said infinite, I meant finite, right? Finite rod, indeed, of length, oops, I don't want thick anymore, of total length L. There we go. Okay, so I'm going to choose the left end. Let's just make that, I don't know, point P. At some distance, I'll call it Z above that end. That's the Z-axis. This we'll call the X-axis. And so if this rod creates an electric field, that means it has to have some amount of charge, right? And so this is a one-dimensional object, so thus it has some amount of charge density, which we can write as dq per dx. In other words, charge per unit length. You may see problems in the future when you do, in fact you will, when doing these types of problems. One-dimensional objects will have charge densities denoted by a lambda, and so by convention, that's just what it is. 1D is lambda. For 2D objects, like a disk, that's the symbol or the variable sigma. So lambda for a line, if you will, sigma for a surface. And if you're really gung-ho and your teacher is really, really strict and harsh and terrible, he'll assign a problem with a three-dimensional object. And in that case, you have a charge per unit volume, and that's the Greek letter rho. So sorry for that one. You don't have a nice memory aid, but just for future reference. All right, back to our problem. This rod of total length L has some charge density lambda, and that's constant, right? That's a uniform charge density. It does not matter how much or how large the chunk. You can break it up into an infinitely small chunk just on the left side, or your chunk can be, say, this long, right? The ratio of charge per whatever length that charge encompasses is the same, okay? And so now in this problem, if we want to calculate the expression for the electric field at this point in space, well, all of the charges in this rod are creating their own electric fields at that point P in space, right? There's some dq of just the leftmost part of this rod sending the electric field, and they have its own vector pointing up, right? At the whoops, I tapped the screen. At the part just to the right of it, over here, it has a different distance to it. And so the distance is no longer z like it was over here. It's a little bit larger, right? So the electric field may be a little bit smaller, right? If you move way over here, it's even further away, right? So the electric field would be a little bit smaller even still. So what we'll ultimately try and do is take all of those chunks of the rod and add them up from, say, 0 to L. And we'll have one, I'll say nice expression, okay? But we'll make sense of it as we go along, okay? So let's just choose a hypothetical chunk right there. We'll call this chunk dx, right? We've chopped it up into some differential amount dx. That is a distance from the left of x, that, okay? And that differential chunk is a distance from the point P I'll call lowercase r. Okay, so if you notice, we have a right triangle here. We can call that theta. That'll come in handy later. And so that little differential chunk dx creates an electric field at point P that points in that direction. We can call that DE, right? And so yes, if you want to translate the angles, you can. And then of course that DE is some superposition of X and Z components, right? So now that we have some general location dx and that respective distance r, which by the way we can write in terms of x and z, right? Now we can get to actually writing out the Coulomb's law, right? The electric field for this rod in question. Okay. All right. In these problems, you may have already seen a pattern, right? We can't exactly use symmetry like the problem where you calculated the field above the center of the rod. So we have to get a little more clever, right? In these problems, the first thing you should try and do is determine what type of charge density it has. Is it linear? Is it a surface? Or is it a volume? Okay. Once you can do that, then you can rewrite that expression and solve for dq. Okay, done. Easy. Okay. The next thing is you should, well, determine everything about the geometry that you can. So for instance, I wrote out this distance from the chunk in question to the point in question in terms of the other distances in the problem. In this case, x and z. Okay, this is a right triangle, and so using a Pythagorean theorem, we can do that. Okay? And now we're using those pieces when we piece together the electric field. Okay? So finally, the electric field is, well, integral of all of those dEs. We're going to start out fairly general here, right? Remember this dE up here, this differential value of the electric field is due to just this little chunk, right? And so this location on this rod has this value of lowercase r. Well, what about this position? That has a different lowercase r, we'll say, right? So what we have to do is integrate from the left side to the right side and effectively add up all of these dx's and thus all of these dEs to get the total E, right? The total electric field. All right. So let's write this out in both the components also. Right? That direction, the left and up at the same time, that's going in the negative, the negative x direction. So we'll say negative, how do I want to do this? dE, let's do x in the I hat direction, and then it's going up in the plus z direction, so plus integral dE z, j hat. Okay. All right. Coulomb's law. Let's put that up here. K, Q, R squared. Right. To get dE, though, we need to effectively take the derivative. What is changing? What are we breaking up, and what will we integrate over? Well, the Coulomb constant is a constant by definition. And so we have to integrate over our charges, right? The dQs. The dQs is determined by the size of this dx. And as we integrate from the left to the right side, we're effectively changing the amount of dq the entire time. So that is what is being differentiated here. The r squareds will stay as written for right now. Okay. All right, so let's put the first term in terms of what we know. Meaning that term. All right, now we have integral dq r squared. Let's turn this into the actual x component instead of just a subscript. So looking at our picture, right, the x component of this dE vector is pointing to the left. That's the cosine component, right? So we can rewrite it as, whoops, simply a cosine tacked on to the edge or the end. And similarly for the z component. Whoops, I have j hat. To be consistent, I should have k hat. X is with I, y is with j, z is with k. Okay, k integral dq r squared. That's going up, so that's the sine component, sine theta. K hat. Okay. And so let's solve for each of these terms individually. It'll get a little bit messy if we try and keep it in one line. Not to mention, I may run out of room. All right, so, whoops. Oh, I guess that didn't matter. So the x component, we have minus k, and then we had the integral of dq times cosine. Well, dq, looking up here, is lambda dx. And cosine, well, we'll figure that out in 1 second. Lambda dx, I'll keep r squared there. Cosine from that triangle, adjacent over hypotenuse. The adjacent is x, and the hypotenuse is r, but we should put it in terms of x for reasons you'll see in a second. So that's our cosine. Okay, now r squared, if that's r, square that, and we have just the regular x squared plus z squared. Right? And so again, this is in the x direction, I hat. And so what we effectively have is this. The k constant comes out, the lambda is constant, that comes out of the integral. And so we have x divided by combining denominators, x squared plus z squared over 3/2 times dx, right? That becomes a 3/2 power because this here, this first denominator is effectively a power of 2 over 2, and then this square root has a power of 1/2. So we're combining those, meaning we add exponents, we have 3/2 power on the bottom. Okay, and so this integral, you may recoil in horror by it. You can look it up. It should be in your textbook. You don't have to do it by hand. That is, if you don't want to, at least. Well, actually, before we write out the next line, what are the limits of integration? Well, we're going from the length of the entire bar, so the far left side to the far right side. That is a distance of capital L. 0 to L. Okay, and so let's see. I've looked this up before. So we have the following. Brackets now. We have so that's what the integral it actually becomes a negative, right? So now evaluating the limits gives us, well, let's see, I'm going to keep the negative k lambda out front for right now. Minus 1 over plugging L in for x, since that was the variable. Whoops. This still stays a square root. And then we plug in 0, so we're subtracting a negative. 0 squared and so this becomes, I'm going to rearrange this, taking these into both sides gives us the following. And then plus, this is 1 over z. Right? Oh, I hat. So this is our answer for the x component. Okay. It's a little ugly, but we'll reevaluate it once we get the z component. Okay. So speaking of, let's do EZ. EZ was the same thing but with sign. So we have k integral dq was lambda dx, and the r squared was the same as above. Sine is opposite over hypotenuse, so z over r. I'll keep it in powers now. And so here, we can rewrite this as k, whoops, yeah, that's right, k lambda integral of, well, I guess z is constant too. Evaluated from 0 to L. So even though this is the z component, we're still evaluating across the exact same limits, right? And across the exact same variable, dx, right? Because that's, well, what the actual rod is, right? All right, this one, a little bit different integration. I'll just write down what we get. K lambda z times x over z squared, and then the square root. Zero to L. Okay. And so here it becomes k lambda, and then I'm just going to do it like this. And then one last thing, we have this as over z. That's the difference here. So we have a final expression of that for the z component, and this for the x component, right? And so if we evaluate what, let's see, if hypothetically this point P in question were very, very far from that rod in the z direction, right? If it was an infinitely far distance upwards, we'll say. So if if z is much, much greater than L, how does that change our answers? Well, if z is much, much greater than L, it's an infinite distance upwards. The rod still has the same orientation. How does that change our answers? Well, z would basically go to infinity there, and the value for L stays the same. So thus that's 1 over infinity plus 1 over infinity. That's basically 0. So that goes to 0. The z component gets a little bit trickier. Z is still going to infinity, but L stays the same. L doesn't cancel out now. But, well, let's see. Let's see, that goes 1 over infinity squared. That's 1 over infinity. 1 over infinity cubed. But that's 1 over square root of z squared. So that acts as 1 over z times another 1 over z right here. So actually what happens, oops, I need more space than I thought. Ez becomes k lambda, where was it? L over, I'm going to combine terms now, z squared. K lambda times L over z squared, and this is in the z direction, or k hat direction. Let's take a look. What is lambda times L? Oh, gosh darn it. What is lambda times L? That's the charge density, charge per unit length, times a length. Lambda L is just Q. And so what we effectively have is KQ over Z squared. And that's a point charge. That's what we have there. I got to get better at that. So if Z is much, much greater than L, right? If that point P in question is very far away, upwards from this rod, that rod basically looks like a point, okay? So hopefully this has given you a little bit of further practice in the steps to try and determine the electric field's a distance from various objects, right? There was no symmetry in this problem. We purely took into account the geometry, right, in terms of the distance from the DQ in question to the point P in question, right? I called that lowercase r, and the distances x and z, and the charge density of the object. The only way this worked so nicely is because the charge density was uniform. Okay? If it wasn't, it'd be hairier, right? It'd be a lot tougher problem. Okay? So that bit plus the charge density, and we got rather complicated answers, but hopefully I made some sense of them. All right, thanks for watching.